Welcome to the deep dive. Today we're tackling a really powerful, though maybe sometimes overlooked, part of Python, bitwise operators and data type modifiers.
Hmm.
We've got a pretty comprehensive breakdown of these tools, and, well, for you, the learner, our goal is really to pull out the crucial insights, how they work, why they're valuable.
And keep it clear, right?
Exactly. Keep it engaging. Think of this as like your fast track to understanding a side of Python that can unlock some significant efficiency and control in your code.
Absolutely. We're going to explore the core principles, yeah?
Yeah.
And the practical applications where these things really shine.
hmm
And maybe some smart ways to use both the bitwise operators and Python's data type flexibility. The aim is that you'll walk away not just knowing what these are, but really getting where they give you an edge, those little aha moments.
Those are the best. Okay, let's dive right into bitwise operators then. Now, the fundamental idea here, it's that instead of working with numbers in their usual decimal
I
form,
go deeper.
right, these operators go straight to the binary, the actual zeros and ones that represent the number, at the computer's level.
And what's fascinating there is by operating directly on these binary digits, these bits, we gain this incredibly precise control over the data.
Precise how?
Well, Python gives us a set of these operators. There's the AND operator, that's the AND symbol,
Right.
and the OR operator, which is the pipe symbol.
Yeah.
Think of this low-level access as being able to, tweak the very building blocks of your data.
And these aren't just, theoretical concepts. The sources we're looking at, they really highlight that these operators are used in a ton of real-world scenarios.
Oh, yeah, like what?
Well, stuff like making graphics run smoothly, ensuring reliable network communication, even in cryptography.
Ah, oh, yeah.
All because they allow for super efficient data handling.
And if we connect that to the bigger picture, you can kind of see why manipulating data at the binary level often gives you a speed advantage.
Yeah.
When you're working with individual bits, these operations can be significantly faster than, say, standard arithmetic that deals with the whole number at once.
Mm.
Imagine it like flipping a single light switch versus adjusting a whole dimmer dial once, just inherently quicker.
Yeah, that's a great analogy. Simpler actions at the most basic level, they should be faster. And it's not just about speed, is it? The material also emphasizes how these bitwise operators are key for optimizing memory use.
Exactly, which is super critical in environments where memory is tight.
hmm
Embedded systems, maybe?
Could be, yeah, anywhere memory's a premium.
Precisely. So how do we actually use these? Let's start with the bitwise AND operator, the AND.
Okay.
The analysis explains this performs a logical AND on each pair of corresponding bits. So for any two bits you're comparing,
Uh-huh.
the result is 1 only if both of them are 1. Otherwise, it's 0. Think of it like a very strict gatekeeper. Both conditions must be true to pass.
Right. And we've got a great illustration here. 10 and 7.
Okay?
In binary, 10 is 1010 and 7 is 0111. So if you compare each position, let's see. Only in the second position from the right are both bits 1.
Oh, okay.
So the binary result is 0010, which is just 2 in decimal.
And what's particularly useful about this, as the sources point out, is how it's often used to, clear specific bits, or to check the status of bit flags in lower-level programming.
Bit flags, like permissions.
Exactly. Imagine you have a set of permissions encoded as bits read, write, execute, maybe. The AND operator lets you precisely check if a particular permission is set without messing up the others.
Ah, I see. So you'd AND it with a mask that only has that one permission bit set.
You got it. Think of it as your precise digital scalpel. You can isolate and inspect individual bits with, surgical accuracy, really crucial for tasks like checking those permissions.
Okay. Like determining if a user has read and write access if those are just single bits somewhere.
Perfect example.
Now let's look at the bitwise OR operator. That's the pipe B. The analysis tells us this operator sets a bit to 1 if at least one of the corresponding bits is 1, so it's a bit more permissive.
Yeah, exactly. A bit more lenient than AND. Taking our previous example, 10 or 7, that's binary 1010 or 0111,
Uh-huh.
results in 1111 in binary, which is 15 in decimal.
Why? Oh, because in every position, at least one of the original numbers had a 1.
Precisely. One or the other, or both.
And a key application of OR, according to our source, is in combining bit masks.
Right.
This lets you set multiple flags at once, so if you want to grant both read and write permission.
You'd OR the existing permissions with a mask that has both read and write bits set to 1.
Gotcha. It's also really handy for enabling specific features in configuration settings, right? You can just
Yeah.
OR in the bit for that feature without affecting any other setting.
Exactly.
Sorry.
Super useful for configuration flags.
Okay, next up is XOR.
Yep, the bitwise XOR operator represented by the caret. Now this one's interesting because it returns 1 only when the corresponding bits are different.
Different. Oh, so 1 and 0 gives 1, but 1 and 1 gives 0.
You got it. And 0 also gives 0, only different bits result in a 1. Think of it as a detector of differences.
So 10 XOR 7, that's binary 110 XOR 0111.
Okay, walk me through it.
Let's see. First bits 1 and 0 are different, so 1. Second 0 and 1 are different, so 1. Third 1 and 1 are the same, so 0. Fourth 0, 0, and they're the same, so 0. Wait, did I do that right? No, hold on. 1, 0, 1, 1, 11.
Let's recheck rightmost. 0, 1 is 1. Next, 1, 1 is 0. Next, 0, 1 is 1. Leftmost, 1, 0 is 1.
Ah, okay, so 11 and 1, which is 8 plus 4 plus 1.13 in decimal. Thanks.
No problem. And what's really clever about XOR is its applications. The analysis highlights that it's a key operator in algorithms that need to toggle bits.
Toggle, how does that work?
Well, if you XOR a bit with 1, it flips it. 0 becomes 1, 1 becomes 0. If you XOR with 0, it stays the same.
Oh, interesting.
So you can use it to flip specific bits on and off. It's also valuable in parity checks, a simple way to detect errors in data transmission.
And here's where it gets really interesting, I thought. XOR is even used in some basic encryption methods.
That's right. The source mentions XOR encryption. You use the operator to flip bits based on a secret key. And the cool part is, applying the exact same XOR operation again with the same key reverses the process.
So it encrypts and decrypts with the same step.
Exactly. Simple, but effective in some contexts.
Wow. Okay, what's left? The not operator.
Yep, the bitwise not operator, the tilde. This is the one's complement operator, and it basically flips all the bits of an integer. Zeros become ones, ones become zeros.
Well, it gives us a unique way to do a kind of negation at the bit level.
Right. The example given is 10. The analysis says this results in -11.
Minus 11. How does flipping bits give a negative number?
This involves how computers typically represent negative numbers, using something called 2's complement.
Okay.
So 10 in binary, let's say using 8 bits for simplicity, is 000000010 back.
Right.
Applying not flips every bit, so you get 101, 110, 101.
Okay, I see the flip, but why is that ag and 11?
In the 2's complement system, that specific pattern, 111101001, represents the value -11. It's a standard convention. The leading one usually signifies a negative number in this system.
Okay, that's a bit more involved, but the core idea is that not flips all the bits.
Exactly. The source emphasizes this is essential for bitwise negation and pops up in various low-level computational tasks. The key takeaway is the bit flipping. The 2's complement part explains the negative result.
Got it. And finally, we have the shift operators.
Right, the bitwise shift operators.
Yeah.
Left shift and right shift. These literally move the bits of an integer to the left or right by a specific number of places.
Okay, so left shift row.
That effectively multiplies the integer by 2, raised to the power of the number you're shifting by. So xn is basically by 2n.
Oh, okay. Quick multiplication by powers of 2?
Yep. And the right shift operator does the opposite. It divides by 2 to the power of the shift amount.
Divides. What happens to bits that fall off the end?
Crucially, any bits shifted off the right end are just discarded. Lost.
Huh. The analysis gives an example. 10-2.
Okay, so 10 is binary 1010.
Shift it right by 2 places.
Yeah.
The 1 and 0 on the right fall off,
Leaving.
leaving 0010, which is 2 in decimal.
Exactly. Those 2 bits just vanished.
And what's really efficient about these, the source says, is how they can optimize arithmetic.
Totally. Multiplying or dividing by powers of 2 using shifts is often much faster at the hardware level than using standard multiplication or division instructions.
So for performance-critical code, especially inside loops,
These can be incredibly valuable. Think of them as hardware-level shortcuts for those specific multiplications and divisions.
our source also gives some practical scenarios where you might use all these operators. We're talking things like toggling specific bits on or off within a value.
Like we saw with XOR.
Right. Setting particular flags in a data structure using masking techniques with A&D to isolate certain bits, that kind of thing.
Yeah, standard bit manipulation tasks. And here's a more advanced point. Python actually lets you customize how these bitwise operators behave for your own custom objects.
Operator overloading, right.
Exactly. The analysis mentions that within your custom classes, you can define special methods. things like and, or, XOR.
And those correspond to N and SAR and ET.
Precisely. So you could define exactly what happens when you use those operators with instances of your class.
Why would you do that?
Well, these customizations let you tailor the bitwise behavior to the specific internal logic of your objects. It makes your objects interact maybe more intuitively within a certain problem domain.
Can you give an example?
Sure. If you had an object representing, say, a set of network configuration flags, you could overload the operator so that using it naturally combines the flags from two configuration objects.
Ah, okay. So it extends the usefulness of objects in very specific situations. The source even mentions using bit masks with and for controlling hardware registers efficiently.
Yeah, that's a classic low-level application.
Yeah.
And as we mentioned earlier, a key thing is that these bitwise operations are generally very computationally lightweight, cheap.
Making them great for tasks that happen a lot, high-frequency stuff.
Definitely.
Okay, cool. So, shifting gears now. Let's delve into data type modifiers in Python.
Right. A fundamental aspect of Python here is its dynamic typing, meaning the data type associated with a variable isn't fixed when you first define it. It can actually change as your program runs. You can assign an integer to X and later assign a string to X.
In this flexibility, it often leads to what the source calls implicit conversions.
Yeah, these happen automatically in many situations. Python tries to be helpful, basically.
How so?
Well, it tries to let operations proceed smoothly without causing errors or data loss where possible. The example given is adding an integer to a float, like 123 plus 1.23.
What happens there?
Python will automatically, implicitly, convert the integer 123 to a float 123.eo first.
Ah, so it can add the two floats.
Exactly. So the result, 124.23, is also a float. It does this promotion to float to avoid losing the 0.23 part. It's trying to maintain data integrity.
Okay, that seems handy. But does it always work?
Well, this implicit conversion is intended to be seamless, yeah, and prevent loss of precision in common cases. But the source also highlights its limitations. It won't work if you try to combine fundamentally incompatible types. Like, you can't just add the string hello and the integer 5 implicitly. Python doesn't know what you mean.
Right, that would need explicit instructions.
Precisely. That's where explicit conversions come in. Here, you, the programmer, use specific built-in functions.
Like int, float.
Exactly,
Okay.
those.
Yeah.
You use them to intentionally transform a value from one data type to another. For instance, if you get user input, it often comes in as a string, right?
Yeah.
Like 1, 2, 3.
Yeah.
If you want to do math with it, you first have to explicitly convert it using int 1, 2, 3.
That's called typecasting.
Yep, typecasting. It's essential for telling Python exactly how you want to interpret that data.
The analysis really underscores the importance of this, especially, like you said, with user input, or maybe when talking to external systems, APIs.
Right. APIs often expect data in a very specific format. So being explicit about the type ensures your program interacts correctly. No guesswork.
Now, implicit conversions tried to prevent data loss, but the source warns we need to be more cautious with explicit conversions.
Absolutely. For example, converting a float to an integer using int. If you have 3.14 and you do int 3.14,
It becomes just 3.
right, it truncates the decimal part completely. That's a potential loss of precision you need to be aware of. Sometimes it's what you want, sometimes it's not.
And there's also the risk of errors, isn't there?
Definitely. What's crucial here is the potential for a value error. The analysis specifically mentions this. For example, if you try intet 12.3,
That's a string with a decimal point.
right, Python will raise a value error because 12.3 isn't a valid literal representation of a whole integer.
So what do you do then?
Well, the source suggests maybe taking intermediate steps. If you have 12.3, you could perhaps first convert it to a float using float 12.3.
Which would work, giving you 12.3.
Right. And then, if your logic requires an integer, you could convert that float to an integer using int 12.3, knowing it will truncate to 12.
Okay.
Yeah.
That makes sense. Requires a couple of steps.
And to handle the possibility that the initial conversion might fail, like if the string was hello instead of 12.3, the analysis recommends using try-except blocks.
Ah, error handling.
Exactly. You wrap the conversion attempt in a try block,
Yeah.
and in the accept value error block, you put the code that should run if the conversion fails. It stops your program from crashing.
It's the code more robust. Good idea.
Very much so. It's a way of saying, try this conversion, and if it blows up with a value error, don't panic, just do this instead.
Now, we can't really talk data types in Python without mentioning pandas, right? Especially for data analysis.
Oh, absolutely not. Pandas is huge, and the source highlights how pandas gives you a really powerful way to change data types for entire columns in a data frame.
using the ASType method.
That's the one, .astype. It's incredibly useful for ensuring consistency and often efficiency when you're working with tables of data.
So if a column gets read in as, say, generic object type, maybe because it had some strings mixed with numbers.
You can use that as type to force it into the type you need. Maybe you clean it up first, then you could do, say, dfmycolumn.astype float32 to make it all 32-bit floating point numbers.
Or like a stype for a column of zeros and ones.
Perfect, yeah.
Yeah.
And strategically using astype to maybe downcast types, like using float32 instead of the default float64, or in16 instead of in64.
That saves memory, right.
Hugely, especially with massive data sets. You can dramatically shrink your memory footprint, which often translates directly to faster processing and maybe even lower costs if you're in the cloud.
So converting types in pandas isn't just about correctness, it's also a key optimization technique.
Definitely both, correctness and performance.
One important detail, though, the source mentions ASType doesn't change the data frame directly.
That's a key point. By default, astype returns a new series or data frame with the changed types. It doesn't modify the original one in place.
So if you want the change to stick.
You need to assign the result back.
Yeah.
Like dfmycolumn is dfmycolumn.astype.
Got it. Okay, so conversions are necessary, powerful. But the source also mentions potential performance issues.
Yeah, it's a balance. While often necessary, doing excessive type conversions, especially if they happen repeatedly, like inside a tight loop processing lots of data,
That can slow things down.
it can introduce overhead, yeah. Each conversion takes some amount of processing time. If you do millions of them, it adds up.
And it's not just the explicit ones like .asus type up, the implicit ones can have effects too.
Right. The analysis mentions implicit type promotions,
Yeah.
like that into float thing we discussed earlier.
Yeah.
If you're doing tons of mixed type arithmetic, those automatic promotions, while convenient, could add some minor processing steps that might matter in very high performance scenarios.
So it feels like there's this trade-off. Developers need to balance the convenience of Python's dynamic typing and its helpful implicit conversions.
With the need for absolute precision and optimal performance, which might push you towards more deliberate explicit typecasting sometimes.
And the source really emphasizes using Pandas as size type when you're dealing with structured data like data frames. It's the right tool for that job.
For sure. Ultimately, a good understanding of how and when to convert types just leads to much more robust, reliable, and performant code.
Which brings us nicely to best practices and maybe a closer look at those performance considerations.
Right. The analysis kind of sums it up. Implicit conversion. Simple code, generally. But watch out for those unintended promotions.
Like the example of integers suddenly becoming floats in scientific calculations, potentially messing up results.
Exactly. That's the kind of subtle risk you might face if you rely only on implicit conversions everywhere.
On the flip side, explicit conversion makes your intent really clear in the code. It's obvious what you're doing.
But as we said, you got to handle it carefully. Avoid unexpected errors with try except.
And be aware of potential data loss, like truncating floats to ints using int. That loss of decimal info can really matter sometimes.
Absolutely. Precision matters.
And in pandas, the best practice seems clear. Use .astype, maybe even provide a dictionary of D-types for multiple columns at once to get everything in the right format.
Yeah, that ensures your columns have the correct and likely most memory-efficient format for whatever analysis or processing you're doing next. Helps correctness and speed.
And if you are worried about performance, especially with conversions,
Then profiling is key. The analysis stresses using tools like cprofile in Python.
to actually measure where time is being spent.
Exactly. To identify real bottlenecks. Maybe those frequent .type calls in your data pipeline are causing a slowdown. Or maybe it's something else entirely. Profiling tells you where to focus your optimization efforts.
Good point. Don't guess, measure.
Always. And it's worth just quickly reiterating, the bitwise operations themselves, generally very fast.
Because they're low level.
Yeah, they map very closely to what the processor actually does. Computationally inexpensive, great for those high-frequency tasks where every microsecond might count.
Looking ahead slightly, the analysis mentions potential future developments. Operator overloading getting even better.
Yeah, it touches on the possibility of future enhancements in Python that might give even more flexibility there.
And maybe more granular type modifiers.
Possibly. Stuff that could expand Python's versatility even further, maybe in areas like systems programming or more complex data science, where super fine-grained control over types and operations could be beneficial.
Interesting. So wrapping it up, the source concludes that fundamentally, Both bitwise operators and data type modifiers are pretty essential tools for effective Python programming.
Yeah, there are different facets of controlling your data. Mastering bitwise ops gives you that low-level precision, that potential for performance tuning.
While understanding type conversion, both implicit and explicit, ensures your data handling is robust, predictable, and you avoid common pitfalls.
And like we said, the key is often finding that right balance. Leveraging Python's convenience where it makes sense, but stepping in with explicit control when precision or performance demands it.
So, to sum it all up for you, the learner, hopefully you now have a much clearer picture of how these bitwise operators work their magic down at the binary level.
Offering those efficiencies in memory and at speed,
Mhm.
yeah. In areas like graphics, networking, that sort of thing.
Exactly. And we've also explored how Python's dynamic typing and its data type modifiers give you flexibility.
But also requires some careful thought about performance and potential errors.
Right. We dug into the specifics AND or XOR, not two, the shift operators, and we really highlighted the significance of both implicit and explicit type conversions.
Especially when you're using powerful libraries like pandas. Knowing .as type is crucial there.
Definitely. This deep dive should give you a really strong foundation.
Yeah, and as you continue your journey with Python, I'd really encourage you to, maybe explore some specific real-world uses of bitwise operators. Maybe dig into network protocols or look at simple cryptography examples.
Or on the other side, experiment. See the actual performance difference between implicit and explicit type conversions in your own code. Try it on some larger data sets.
That's a great way to learn. Which kind of leads to a final thought for you to chew on.
Oh.
In what specific kinds of programming challenges, maybe ones you've faced or can imagine, do you think having that really detailed bit level control we talked about,
Mm.
where could that lead to the most, I don't know, surprising or significant advantages?
Mm. Where could manipulating individual bits make a really unexpected difference? That's a great question to ponder.
Definitely something worth thinking about.